Here's a question that sounds almost childish until you actually think about it. Can a moon have its own moon? Planets have moons. We know that. Jupiter has nearly 100 of them. Saturn has over 140. Even tiny Pluto has 5. Moons are everywhere in our solar system, hundreds of them, orbiting everything from gas giants to dwarf planets. But what about the moons themselves? Could a moon have a smaller object orbiting it? A satellite of a satellite? The answer is surprisingly interesting. It's not just a matter of yes or no. It depends on physics, orbital mechanics, tidal forces, and the specific properties of the system in question. In this video, we'll break it down. What would it take for a moon to hold its own satellite? Do any moons in our solar system qualify? What about moons around planets in other star systems? And if such objects exist, what should we even call them? Let's find out. Let's start with something straightforward and uncontroversial. Yes, it is absolutely possible to put a small object in orbit around a moon. We know this for certain because humans have been doing it since the 1960s. In March of 1966, the Soviet mission Luna 10 became the first spacecraft to successfully enter orbit around our moon. It completed more than 460 orbits before its mission ended. Since then, we sent dozens of spacecraft into lunar orbit. NASA's Lunar Reconnaissance Orbiter launched in 2009 and is still operating today, mapping the moon in extraordinary detail. And in 2024, construction began on the Lunar Gateway, a space station that will orbit the moon as part of NASA's Artemis program, serving as a staging point for future lunar surface missions. So, artificial satellites around moons? Absolutely proven, no question. But these are small, human-made objects with short mission lifespans. The real question is more ambitious. Can natural satellites, actual moons formed by geological and gravitational processes, orbit other moons? And could such a system remain stable, not just for months or years, but for billions of years? Before we dive deeper, let's establish some terminology. A natural satellite that orbits another natural satellite would technically be called a subsatellite. In more informal scientific literature and definitely on the internet, it's often called a submoon. The internet has enthusiastically suggested other names: moon, moon squared, moon cube for even deeper nesting, mini moon, and various other creative options. But most scientists prefer submoon because it follows the same logical pattern as other astronomical terminology: subsatellite, substellar, subgiant, and so on. Here's the key physical concept you need to understand. Every massive body has a region of space around it where its gravity is dominant over external influences. For a planet orbiting a star, this region is called the Hill sphere. Within the Hill sphere, the planet's gravity is strong enough to hold onto moons despite the star's gravitational pull. The same principle applies at every level. A moon orbiting a planet also has its own Hill sphere, a smaller region where the moon's gravity dominates over the planet's gravity. If a submoon orbits within that region, and if it's small enough that it doesn't destabilize the system through tidal interactions, it could theoretically survive for long periods. The question is, under what specific conditions is long-term stability actually achievable? Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show the next videos, and you'll miss what we uncover next. Putting something in orbit around a moon isn't particularly difficult. The challenge is keeping it there for astronomically relevant timescales, millions or billions of years. There are two fundamental ways a submoon can be lost. One, it drifts too close to the host moon. If this happens, the submoon can either crash into the moon's surface or get tidally ripped apart once it crosses inside the Roche limit, the distance at which tidal forces overcome the submoon's own gravity holding it together. Two, it drifts too far away. If the submoon migrates outside the moon's Hill sphere, the planet's gravity becomes dominant and effectively steals it, either ejecting it from the system or pulling it into a new orbit around the planet itself. The critical insight is that orbits don't stay static. They evolve over time due to tidal forces. You're already familiar with this from Earth. Our moon is slowly moving away from us. The current rate is about 1.5 inches per year. Small, but measurable with laser reflectors left on the lunar surface by Apollo astronauts. Why does this happen? Because the moon raises tides on Earth. The tidal bulges on Earth don't align perfectly with the moon. They lead slightly ahead because Earth rotates faster than the moon orbits. This configuration gradually transfers angular momentum from Earth's rotation to the moon's orbit, pushing the moon outward. The same physics applies to submoons. A submoon would raise tides on its host moon. Those tides would cause the submoon's orbit to evolve, either outward or inward, depending on the relative rotation and orbital rates. If the submoon is too massive, this tidal evolution happens too quickly. The submoon either escapes the Hill sphere or crashes into the host moon before a billion years pass. That's the key constraint. Not just whether a submoon can exist, but whether it can persist. In 2019, astronomers Juna Kohlmeier and Sean Raymond published a detailed theoretical analysis of this question. Their paper systematically explained which moons in our solar system and which hypothetical moons around exoplanets could theoretically hold onto submoons for billions of years. The analysis started from existing theories of tidal evolution that were developed decades earlier, particularly work by Barnes and O'Brien in 2002. Kohlmeier and Raymond essentially took that framework and applied it to the submoon problem. They found that two factors matter most. One, the moon must be far enough from its host planet. The farther out a moon orbits, the larger its Hill sphere becomes because the planet's gravitational influence weakens with distance. A larger Hill sphere means more room for a submoon to exist in a stable zone. 2, the moon must be large enough. Larger moons have stronger gravity and therefore larger Hill spheres. They can hold on to bigger submoons and maintain stability despite tidal evolution. Based on their calculations, 4 moons in our solar system emerge as theoretical submoon hosts. Iapetus, Saturn's third largest moon, orbiting very far from the planet, actually the best candidate. Titan, Saturn's largest moon, massive but closer to Saturn than Iapetus. Callisto, Jupiter's second largest moon in a wide orbit. Earth's moon, large and at a reasonable distance from Earth. According to their model, Iapetus could theoretically hold onto a submoon up to 120 miles in radius. That's approximately the size of Saturn's moon Mimas. Not a trivial pebble, but a substantial object. Interestingly, Iapetus outperforms even Titan despite being much smaller. The key is its extremely distant orbit from Saturn, which gives it a proportionally enormous Hill sphere. Here's the puzzle. If Iapetus, Titan, Callisto, and our moon could all theoretically host submoons today, why haven't we observed any? We've mapped these moons extensively. Cassini spent years in the Saturn system. Galileo and Juno studied the Jupiter system. We have detailed surveys of every major moon in the outer solar system. No submoons. There are several possible explanations. 1, they never formed in the first place. Submoons would need to form through the same basic processes that create regular moons: capture of passing objects, collision and accretion, or co-formation from debris disks. Perhaps those conditions simply never occurred around these specific moons. Maybe the environments around moons aren't conducive to capturing or retaining small bodies. 2, they formed but were lost during the moon's orbital evolution. This is important. Remember that moons migrate over time. Iapetus, for example, may have formed much closer to Saturn and only migrated outward to its current distant orbit. When it was closer to Saturn, its Hill sphere would have been much smaller, potentially too small to hold onto any submoon. Any early submoons would have been lost before Iapetus reached its current position. 3, they exist, but we haven't detected them yet. Submoons would be small and faint. Our surveys have limits. It's possible that very small submoons exist around some moons, and we simply haven't found them. The absence of observed submoons doesn't prove they're impossible. It just tells us something about the history and conditions in our specific solar system. There's an intriguing observational detail about Iapetus that might be relevant to this discussion. Iapetus has a massive mountain ridge running along its equator. This ridge reaches heights of up to 12 miles in some places, taller than any mountain on Earth, and extends for over 800 miles along the Moon's equator. It is one of the most bizarre and unexplained geological features on any moon in the solar system. In 2011, researchers proposed an intriguing hypothesis. What if something large crashed into Iapetus long ago, creating both a temporary submoon and a ring of debris orbiting the moon? According to this model, the submoon would have experienced tidal evolution. It would have migrated outward over time and eventually escaped Iapetus' hill sphere, just as we've been discussing throughout this video. But the ring of debris would have evolved differently. It would have spiraled inward due to different orbital dynamics. As the debris fell toward Iapetus, it would have accumulated along the equator, exactly where we see the ridge today. This hypothesis isn't proven. There are alternative explanations for the ridge, but it's a fascinating possibility, and it suggests that even if submoons don't last forever, they might leave geological evidence behind long after they're gone. The submoon question becomes considerably more interesting when we look beyond our solar system. In recent years, astronomers have identified 2 potential exomoon candidates, possible moons orbiting planets around other stars. Kepler 1625b I, first announced in 2018. This would be a Neptune-sized moon orbiting a super-Jupiter planet approximately 8,000 light-years away in the constellation Cygnus. Kepler 1708b I, announced in 2022. This would be a smaller, roughly mini Neptune-sized moon orbiting a Jupiter-sized planet. Important caveat that must be stated clearly. As of 2025, neither of these exomoons have been confirmed. They remain candidates, and their existence is actively debated. In December of 2023, a study by Heller and Hipke argued that both candidates are statistically unlikely to be real detections, that the observed signals could be explained by instrumental artifacts and stellar limb darkening effects. In May 2025, the original discovery team, led by David Kipping, published a response defending their analysis and challenging the 2023 rebuttal. Meanwhile, the James Webb Space Telescope observed Kepler 1625b in 2024. That data is still being analyzed as of early 2026. The bottom line, no exomoon has been definitively confirmed to date. The candidates remain candidates. But here's why this matters for submoons. If giant exomoons like Kepler 1625b I do exist, they would be excellent submoon hosts, far better than anything in our solar system. According to Kohlmeier and Raymond's calculations, a Neptune-sized exomoon in a wide orbit could theoretically hold onto a submoon the size of Ceres, about 590 miles in diameter. That's not a small rock. That's the largest object in the asteroid belt. That's a dwarf planet orbiting a moon, orbiting a planet, orbiting a star. If these systems exist, the possibility for complex nested satellite systems become much more interesting. Let's push this concept to its logical extreme. If moons can have moons, can submoons have their own moons? In principle, yes, under the right conditions. Here's a theoretical example that Kohlmeier and Raymond explored. Start with a Sun-like star. Put a super-Jupiter planet around it, say 10 times Jupiter's mass, but not quite heavy enough to be a brown dwarf. Put a Neptune-like moon in a very wide orbit around that planet, maybe 800 planetary radii out, which would still be within half the planet's hill radius and therefore stable. So far, so good. That Neptune-like moon would have plenty of room around it. Now, put an Earth-sized submoon around that Neptune-like moon. According to the calculations, such a submoon could be perfectly stable as long as the host moon is far enough from the planet. And here's where it gets truly wild. That Earth-sized submoon would have its own hill radius, about 135 Earth radii in this configuration. That's enough space to potentially host a submoon of its own. The maximum stable submoon in this scenario would be something like 30 miles in radius, a decent-sized asteroid. So yes, moons of moons of moons are theoretically possible, but you need very specific, carefully tuned parameters to pull it off. Each additional layer requires wider orbits and more precise conditions for long-term stability. Current theoretical models have an important limitation that should be acknowledged. The Kohlmeier and Raymond calculations account for the submoon's orbit evolving due to tidal interactions with its host moon, but they assume the host moon's orbit around the planet stays fixed. In reality, moons also migrate over time due to their own tidal interactions with the planet. A more complete calculation would need to model both motions simultaneously, the submoon migrating relative to the moon and the moon migrating relative to the planet. This would almost certainly reduce the range of stable submoon configurations further, but it probably wouldn't eliminate them entirely. The physics allows for submoons under certain conditions. More refined models would just narrow those conditions. This is an open area for future research. If anyone is looking for a good project in orbital dynamics, this would be a valuable contribution to the field. If we ever discover one of these objects, what do we actually call it? Scientists have proposed several options. Submoon, technically consistent, follows standard naming patterns. Moon, popular online, more playful. Subsatellite, more formal, scientifically precise. Moon squared or moon cubed, for nested levels. There's an interesting argument for dropping the word moon entirely. After all, we don't call moons subplanets or planets. We gave them a distinct name, moon or satellite. Maybe submoons deserve their own unique terminology that doesn't create confusing recursions. But for now, submoon appears to be the term gaining traction in scientific literature. It's clear, it's logical, and it works. You might reasonably ask, why does any of this matter if we haven't actually found a single natural submoon? Because it reveals something profound about the universe and our understanding of it. The calculations demonstrate that entirely new categories of astronomical objects might exist. Objects we've never observed and barely imagined. Moons of moons. Perhaps even moons of moons in exotic extrasolar systems. The absence of submoons in our own solar system isn't evidence that they're impossible anywhere. It might simply reflect the specific information history and orbital evolution of our particular system. Which moons formed where, how they migrated over billions of years, what collision events occurred or didn't occur. Somewhere out there, around some distant star, there might be a giant exomoon hosting its own family of smaller satellites. We simply don't yet have the technology to detect them. Astronomy is the oldest of the sciences. Humans have been studying the sky for thousands of years, and yet we're still discovering entirely new categories of possible objects. Submoons, exomoons, rogue planets, brown dwarfs, quark stars, cosmic strings, and phenomena we've likely never even imagined. For some people, these unknowns might feel frustrating. Perhaps you might wish you'd been born at a time when everything had already been mapped and cataloged. But there's another way to see it. We get to live in an age of discovery, a time when imagination can still wonder, when there are still fundamental questions waiting to be answered. We've barely scratched the surface of what's out there. But here's a related mystery. Not every planet gets to have moons at all. 2 planets in our solar system have none. Mercury and Venus orbit completely alone. No companions, no satellites, nothing. Why? The answer involves gravity, orbital dynamics, and the violent history of the inner solar system. Watch Why Don't Venus and Mercury Have Moons to find out.